It's time to get started. Welcome to another wonderful morning of Chem 1211 with your host, me, Dr. White. And we're going to have a real wonderful morning. Oh, you should see what I've got planned for you. Well, you will. All right. First thing I want to do is go through the problem set for chapter 15, equilibrium, and the Chateliers Principle. Once again, I'm using my north side of Chicago French accent, which means I'm butchering that name. But, anyways, we'll do that, and then we'll do the lab. So let's get started. Everybody see chapter 15 practice? Thank you. All right, these are things you should know. First one, name one of the key factors in the collision theory of reactions that is needed in order for a chemical reaction to occur. You only have to name one, but I give all three. The first one is reactant molecules must collide. That's why it's called the collision theory. And collisions must have enough energy to make a reaction. That's called the activation energy. And finally, for certain molecules, you have to have the proper orientation when they collide. Now, one of the things I do want to mention when you're looking at problems or questions, make sure you read them. And this number two asks what is the activation energy? That's the amount of energy needed to make a reaction occur. Now, how do you make a reaction go faster? Well, I mentioned you can add more reactants. I also mentioned you can increase the reaction temperature. Don't forget the rule of thumb. It's on this thumb. Can you see it? It says for every 10 degrees C increase in the reaction temperature, the reaction rate doubles. I'll say it again. Don't forget the rule of thumb. See it right there? For every 10 degrees increase in the reaction temperature, the reaction rate doubles twice as much. Which is why if you cook a roast at 600 degrees for the same amount you did at 375, you'll come up with a charred mess. So don't. And that's because the reaction rate doubled, more than doubled. Now, there's one I forgot to put there, but what will increase the reaction rate? A catalyst. All right, next, let's talk about energy diagrams. Energy diagrams on the y-axis is energy, and on the x, time. Everybody see the energy diagram on there? Thank you. All right, now, if we look at this reaction, nitrogen plus hydrogen is in equilibrium with ammonia plus heat. And this is an exothermic reaction. And this is a skill you should know how to do. Now, in our world or in our universe, you never create or destroy energy. And therefore, the amount of energy on the reactant side is equal to the total amount of energy on the product side. And if we look at the reactants, nitrogen, hydrogen, it would be here. One thing on an energy diagram, you don't have to put the coefficient like 3 down there. If you want to, that's okay. I won't mark it wrong. Did I tell you I'm this close to the person who grades the test? Me. Now, so we have an initial energy of our reactants. Now, the next question you have to answer is the ammonia, which is the only product you get that you put on an energy diagram, you don't put energy, heat on the diagram, is it more, the same, or less than the energy of the reactants? Well, notice you lose some of the energy as heat, That's what it means when it's on this side. So you're going to have less energy for the ammonia alone than the nitrogen hydrogen, because the energy on the right, or on the reactants on the left, and the products on the right total are always equal. But some of that energy on the product side is lost as heat. So that's why ammonia has less energy. And then you draw a hill, over the hill and down the hill to grandmother, the products we go. And from where you start with the reactants to the top of the hill is the activation energy, which we abbreviate E sub act. And I could have also written here, draw the energy diagram and include the activation energy, which I did. So that's how you do an activation energy diagram for an exothermic reaction. Remember, an exothermic reaction gives off heat. Now, if we look at the next one, water plus heat can break down in equilibrium to hydrogen oxygen. And this is an endothermic reaction or equilibrium. And how do you know that? Because you have to add heat. Heat is on the left side. And again, the total amount of energy on the left side equals the total amount of energy on the right. Now, in an energy diagram, you still have X or Y energy X time. And if we look at water, we pick a arbitrary energy. That's all I've done. Now, are the products more or lower energy than the reactants? Well, since you have to add heat, this is not considered in the energy of water. Adding heat plus water makes the energy of your products in an endothermic reaction higher than the reactants. And again, you have a hill, over the hill and down the hill to products we go, or actually to grandmother's house we go. Somebody let me know what nursery rhyme that came from. I have no idea, I forgot. And again, if I had asked to show the activation energy, it is from where you start to the top of the hill. And that's how much energy you got to take to get over that to go to the products. Now, one of the things I can now show you is the following question. And I'll give you, 10 seconds to think about it. Start. How does a catalyst work? Remember, it's turn on your webcam Friday, please. Pretty please. All right, time's up. Now, most students would say it makes the reaction go faster. Wrong. I didn't ask what does a catalyst do, and I asked how does a catalyst work? And the answer is a catalyst works by lowering the activation energy, making the hill you have to go up much lower. And because of that, then the reaction will go faster because you need less activation energy or lower activation energy. So remember, there are two different questions I can ask. The first one up here, I don't have here, what is a catalyst? And the other one is, how does a catalyst work? By the way, what is a catalyst? It's something that makes the reaction go quicker, but how does it work? It lowers the activation energy. All right, next thing, and if I were to have this on a test, by the way, this number 4 and 5 are incorrect. Now it's correct. And let's look at number 6, which is also incomplete. Now it's complete. It says write the equilibrium constant. KEQ is the equilibrium constant for, and you're given a reaction. Well, how do you do that? Let's go back to chapter 5. Everybody see chapter 5 on their screen? Thank you. And this is the formula used for equilibrium constant. The concentration of the products to the power of the coefficient in the balanced chemical equation, which I always will give you, and you multiply it divided by the concentration of the reactants to the power of the coefficient. Remember, when you put something in a bracket, that means moles per liter or moles per 1,000 milliliters concentration. Now, common mistake, and I'll write it up front, wrong. I don't know why, but students will do something like this. And they put a plus sign, which is wrong. I guess now it's doubly wrong. Yes, it's wrong. And Dr. White marks it wrong. It's a multiplication. Make sure you do that. What I think is they just see this and think it should go there and it should go over here. It doesn't. So that's how you do a equilibrium constant. So let's look at the problem. And if we look at A, we have sodium oxide in equilibrium with sodium and oxygen. And remember, the products go on top, and the products are the chemicals on the right side, and underneath go the reactants, which are on the left side. In this case, there's only one. And notice I got it right because I'm not doing addition, doing multiplication. So sodium coefficient is 4 to the 4th power times oxygen. When there's no coefficient, it's 1. We don't show it. Divided by sodium oxide to the 2nd power. Now, can everybody see the bottom of the screen B? Can you see? No. All right. I will help out. Can everybody see what I just wrote there? All right, your turn to have some fun. You write the equilibrium constant for what I just wrote, this one right here. Ready, set, go. And all of you turning on your web camera, thank you. And all of you who aren't, could you turn it on, please? Pretty, please. I haven't said that in ages. And if you're having a bad hair day, all right, you don't have to turn it on. Am I having a good hair day? If you think I am, give me a thumbs up. No, you don't have to. Oh, the votes are coming in. And the winner is everybody's done. So let's take a look at how you do that. And notice we have on the right side KCl, potassium chloride, and it's got a coefficient of 2. So we have the concentration of KCl to the second power, and also you have oxygen, the coefficient is 3, oxygen concentration to the third power. And on the reactant side, you have potassium perchlorate, and that's to the second power because of the coefficient. By the way, potassium perchlorate, one of the things you don't know, but Dr. White knows, is that has been for a while used as a propellant by the military for ordnance and rockets. Now, problem with that is, especially on the West Coast in California, when they're decommissioning old ammunition, the potassium chloride, they put in just dumped in a dump site, and that got into the water. And it's, how should I say, polluted the water, which is used to grow things like lettuce and celery. And now, for a number of years now, thank goodness for the EPA, they have found ways to take that out of the water. So the potassium perchlorate, which is a dangerous chemical and not healthy for us to consume in our body, has lowered tremendously. It really affects the people living in those areas who are using it for using the drinking water, which was contaminated with potassium perchlorate. All right, let's continue on. Number 7, predict the relative amounts of reactants and products for the following equilibrium when you're given the equilibrium constant KEQ. And remember, hang in there. If anybody has a better saying I can say while I'm telling you to just be patient and wait, let me know. I guess I could just say, be patient and wait now. All right, everybody, in a simplified concept, KEQ, the equilibrium constant, deals with the product concentrations divided by the reactants. So if KEQ is much greater than 1, therefore the top of this is going to be larger than the bottom to get this to be a larger number. And therefore we know that's what these 4 dots in math mean. Therefore, the products are greater than concentration are greater than the reactants. Now, if KEQ is much less than 1, then the reactants, if I can spell, concentration is greater than the products. And that's because if we look up here, if KEQ is small, the bottom of this fraction, reactants, has to be much larger than the products. So if I asked you something like 3 to 5 points, predict the relative amount of reactants and products for, and notice this number is greater than 1, much greater. And by the way, 3 dots means therefore. See all the cool stuff you're learning from me? Anyways, the products are greater than the reactants. Now, if we look at the next one, we have nitrous oxide going to nitrogen oxygen. And notice this is the KEQ. This is 10 to the minus 34th. And that's a very small number. KEQ is much less than 1. Therefore, the reactants will be greater than the products. All right, can everybody see D at the bottom here? Why don't you do it then? It's sodium oxide is equilibrium with sodium, 4 moles of sodium, 1 mole of oxygen. The equilibrium constant is 1.0 times 10 to the minus 25th. You decide what is the relative amounts of, describe the relative amounts of reactants to products or products to reactants. And when you're done, give me a thumbs up. For those of you who don't have your camera on, use the emoji, which I'm going to be renaming Symboli. I like that better. Don't forget to use your Symboli thumbs up when you're done. Everybody done? Oh, not yet. I think they're done. Let's do it. Now, question is, predict the relative amount of reactants and products for D. And notice K equilibrium is much less than 1. Therefore, when it's less than 1, you'll have more reactants than products. And that's how you do it. Now, let's talk about the Chateliers Principle. Take a deep breath, let it out. This one sometimes can be challenging, but remember, when a system is under stress, it will shift one of those 2 ways to remove the stress. At equilibrium, in a chemical equilibrium, there's a certain amount of the products, reactants, and if it's exo or endothermic heat. And if you change that, guess what? It's going to shift to remove the stress. So let's take a look at that. Oh, speaking about stress, don't forget the lab's due today. Bad, Dr. White. Now I just increased your stress level if you haven't handed it in. All right, now if we look at number 8, everybody see number 8 on their screen? Thank you. We have this equilibrium, and the question is, what happens, and it would be 3 points each, to the oxygen concentration and chlorine concentration if you add more water? Well, at equilibrium, there was a certain amount of, oops, not a certain amount of oops, but a certain amount of chlorine, certain amount of water, certain amount of HCl, hydrochloric acid, and a certain amount of oxygen. Now we've added more water, and now it has too much water and says, oh no, I've got to get rid of some of the excess water. Well, the only way it can get rid of excess water is chlorine reacts with water to go this direction to make more hydrochloric acid, HCl, and oxygen. Now, when something reacts, it's consumed. Remember my French silk pie that I consumed? No, I didn't. I've been good. I haven't even run out and bought one. I've been tempted, but I said, no, I don't. Wait. But anyways, if you add more, this is going to be consumed to get rid of it. So is the chlorine. And when something is consumed, you have less of it, so the concentration will decrease. Now, in order to get rid of the excess water, it reacts with chlorine to go this direction to make more HCl and oxygen. When you make more of something, the amount you have, otherwise known as the concentration, will increase. And that's how you do these type of problems. Now, let's look at number 10. And it's for the following reaction. Now, C6H6, for those who know organic chemistry, Dr. White does, because I am an organic chemist, this has the name benzene. And this compound, C6H12, has the name cyclohexane. Oh, by the way, now you're on my field. And before I go any further, there's 2 things you should know. And those 2 things are an ice bath. When you put a reaction in an ice bath, in other words, make it colder, you're removing heat. When you put a reaction in boiling water, increase the reaction temperature, you're adding heat. So remember, ice bath removes heat, boiling water adds heat. This will not be an important information test number 4. I'm going to make you remember a few things this test. So if we look at number 10, we have this reaction right here, equilibrium reaction. And the question is, what happens to C6H6 benzene and C6H12 cyclohexane if you put the reaction in an ice bath? Oh, by the way, I had it down here too. Boy, am I nice. What does an ice bath do? It removes heat at equilibrium. There was a certain amount of heat, and now you've taken some out. And it says, oh no, I don't have enough heat. I need more heat. And how does this equilibrium make more heat? Benzene C6H6 and hydrogen react to make more cyclohexane and more heat. The equilibrium shifts to this direction. And because of that, the benzene reacting with hydrogen, C6H6, is consumed. And when something is consumed, you have less of it, so the concentration will decrease. Next, when you react the benzene with hydrogen, H2, you'll make more C6H12 cyclohexane. And when you make more of something, guess what? The amount will increase, the concentration increases. Now, if we look at B, what happens to the reaction and what happens to the concentration of benzene and cyclohexane if you put the reaction in boiling water? And boiling water adds heat. And therefore, at equilibrium, we had a certain amount of heat. Now, putting it in boiling water adds heat. And because of that, now the reaction equilibrium says, oh no, I have too much heat. I got to get rid of some of this excess heat. So how does it do that? It shifts this way. Cyclohexane C6H12 reacts with the heat to make more benzene and hydrogen. Well, if C6H12 cyclohexane is reacting with the heat, it's consumed. And because of that, the amount decreases. Now, since you're reacting cyclohexane with heat to make more benzene C6H6, when you make more of something, the amount you have, the concentration will increase. Now, that was for this reaction. If you notice, and I didn't write it down, bad Dr. White, is an exothermic reaction. Because heat is given off, it's on the right side. Now let's look at an endothermic. Oh my goodness, the plus sign fell off. Sorry about that. And this is an endothermic reaction. Because heat is on the left side. Now, once again, it's an equilibrium. At equilibrium, there's a certain amount of CO, carbon monoxide, water plus heat, and it's equilibrium with CO2, carbon dioxide, and hydrogen. And the question is, what happens to CO concentration, hydrogen concentration, when you put it in an ice bath? And remember, an ice bath removes heat. So what I'm doing is, at equilibrium, there's a certain amount of heat. Now we've taken some away, and the react equilibrium says, oh no, I don't have enough heat. I need more heat. And the only way you can replace that heat is by reacting carbon dioxide and hydrogen to make more heat, water, and CO2. Now, if you're reacting the hydrogen with CO2, this is being consumed. When you have something consumed, like the French soak pie, you have less of it, it decreases the amount, the concentration, when it's consumed. Now, while this is being consumed, it's being used to make more heat, but also more carbon monoxide, CO, and therefore it will increase because we're doing A. And that's how you do it. Now let's look at B. You put the reaction in boiling water. And boiling water, what does that do? It adds heat. And at equilibrium, you have a certain amount of CO, water, heat, carbon dioxide, and hydrogen. Now, since we put it in boiling water, we've added heat. And the reaction equilibrium says, oh no, we have too much heat. We've got to get rid of it. Remember, we're doing B now. And therefore, how does it get rid of the excess heat? It reacts with water and carbon dioxide to make more CO2 and hydrogen. And when something reacts, the heat, the water, the CO2, it's consumed, or CO, I'm sorry, and therefore, when you consume something, the concentration will decrease because you've got less. Now, to remove the excess heat, it's going to make carbon dioxide and, excuse me, hydrogen. And if you make more of something, the amount you have, the concentration will increase. And that's how you do it. You know something? I think I'm going to share the fun with you and let you try one. Am I nice? Yes, I am. Why don't you try this one first? What happens to the concentration of A and D if I add more C? And I should ask everybody to see my whiteboard. Thank you. And the votes are starting to come in. And I think everybody's done, so I better get to work. Question is, what happens to concentration of A and D if you add more C? At equilibrium, there's a certain amount of A B, C, and D in heat. And now I've added more C, and the equilibrium says, oh no, we have too much C. Let's get rid of it. How do you get rid of it? A and C in heat react to make more, what did I say? C and D in heat react to make more A and B. And if you react C and D, D is consumed and the amount you have will decrease. And at the same time, we're making more A and B. If you make more of something, the amount you have, the concentration, will increase. Oh, let's have some more fun. Why don't you do B? What happens to the concentration of A and D if you put it in an ice bath? Am I nice today or not, sharing all this fun? If I say fun enough times, you might believe me. And it is. And when you're done, give me a thumbs up. Those of you who don't have your webcam, give me a thumbs up with your, remember a new word I just created, your symboli. All right, I think everybody's done. Let's take a look at B. Now, at equilibrium, there's a certain amount of heat, certain amount of C and D. What does an ice bath do? It removes heat. And therefore, now the equilibrium has less heat and says, oh no, I don't have enough heat. I need more heat. How does it make more heat? A and B react to make more heat, but at the same time, it makes more C and D. So if we look at here, if A and B react, A is consumed. And when something is consumed, you have less than the concentration, the amount you have decreases. And when you make more heat, you're going to make more C and D. When you make more of something, guess what? The amount you have, the concentration, increases. And let's do one more. I'm going to make a little room here so you can still see the equilibrium. And what happens to equilibrium if you put it in a beaker of boiling water? Your turn. And when you're done, give me a thumbs up. All right, I think everybody's done. Let's do this one. And the question is, what happens to the concentration of A and D if I put the reaction in boiling water? And at equilibrium, let me clean this up. Oh no, I just killed A. At equilibrium, there's a certain amount of A, B, C, D, and heat. By putting it in boiling water, boiling water adds heat. So by doing that, we've got too much heat. And the equilibrium says, oh no, I have too much heat. I've got to get rid of it. How can it get rid of it? Heat reacts with C and D to make more A and B. When something reacts, it's consumed. So if heat is consumed, you lower the amount of heat. You're also going to react D, which means the amount of D when you consume something will decrease. And when you react C and D in heat to lower the amount of heat, what are you doing? You're making more A and B. And if I make more A, the amount we have, the concentration, will increase. And that's the Chateliers principle. Now, I got 30 seconds to do something real quick. Dr. White worked for a company, and we did a reaction where we took phenol plus formaldehyde, which has this chemical structure, is in equilibrium with a product we call a resin plus water. And we had a way of removing water, so the equilibrium is shifted this way, and the reaction goes a lot quicker, a lot quicker. Instead of taking days, it only took about 34 hours. Yep, that was still a slow reaction, but without taking the water out, it'd be really slow. Now, what's a resin? It's a fancy name for a glue. And what was that glue used for? It's show and tell time. This is called a dog bone. It's a way of testing a glue when it's used to hold sand together. Where is that done? To make molds for your car engines, where they pour the metal in. And you pull this apart with it's called an instron to measure what's called the tensile strength, how strong the glue is. And this is pretty good. Why do I have this dog? It's called a dog bone. Why do I have this? Because I invented the glue that's holding together the sand. Yay, Dr. White. And this has been used by GM and also Ford. In fact, after I came up with this, which has a much better, it's much more environmentally friendly. When you put the metal in there, the glue after a while burns off, which goes into the air, and it was pretty stinky. And I came up with a way to lower that emissions and make it more environmentally friendly. And I'm going a minute or so afterward, but the people at the Ford Windsor plant that made V8 engines for Ford invited me down to thank me. That was a fun trip. They showed me how they made engines and all that. And I also went to GM plant in Saginaw, which was huge. But with that, oh no, I went a minute and started break. Let's take a 5-minute break, come back at 9:56. I don't want to cheat you out of your minute, and I'll see you in 5. Oops. Oh, you know, I haven't used in a long time. Time to start again. Love that. Come back, wherever you are. All right, everybody back? Or am I just early? All right, let's get started. Excuse me. All right, it's lab time. And today's lab is one Dr. White wrote, and we're going to be using some dangerous chemicals. And today's lab deals with food chemistry. Bet you never thought about it, but food is actually chemicals, various chemical substances. Let me just clean up a little, put something, excuse me, put some things away. All right, does everybody see doing chemistry with food on your screen? Thank you. All right, hold on, I'm gonna have to drink some water. Getting all choked up over this lab. All right, today's lab deals with doing chemistry with food. And all the items that you find in your kitchen or supermarket are chemicals. Yes, chemicals. And the food you eat and ingredients that are used to make the various food dishes or things are composed of atoms and molecules. That's chemistry. And in this lab, we're going to investigate acidity and basicity of various foods and cooking ingredients. And with that, remember, an acid is a proton donor. A base is a proton acceptor. When we talk about terms of acids and bases, we talk about the acidity or basicity of a solution. And what I started teaching you on Wednesday was the pH of the solution, which is an easy way of determining if it's an acidic or basic solution. If the hydronium ion concentration, that should be a sub. H3L plus is greater than the hydroxide, it's acidic. If the hydroxide is greater than the hydronium ion concentration, H3O, then the solution is basic. Now, an easier way to do that is pH. And pH, remember that small p, capital H, is an important measurement chemists use to determine the acidity or basicity of a solution. And the pH is defined as minus the log of the hydronium ion concentration. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's basic. And if the pH I don't have down here is equal to 7, it's neutral. Everybody see my whiteboard? Let's go through this again. pH equals minus the log of the hydronium ion concentration. Now, we have what's called pH paper, and I'll show you that in a second, but let's look at the pH scale. It goes from 0 to 14. In the middle is 7. When you have a pH of 7, that's called the neutral solution because the hydronium ion concentration is equal to the hydroxide ion concentration. When it's less than 7, it's called acidic. And when it's acidic, the hydronium ion concentration is greater than the hydroxide ion concentration. When it's greater than 7, it's called basic, sometimes also called alkaline, but I'll use basic for this class. It's become basic, and that's when the hydroxide ion concentration is greater than the hydronium. Now, the nice thing about pH is you don't have to remember this stuff. You just have to know where the number is. When it's 7, it's neutral. When it's less than 7, it's acidic. When it's greater than 7, it's basic. And that's the beauty of pH. And pH can be measured by different ways. One is a pH meter, which we will not be using. Now, the way you'll be measuring pH is using pH paper. If any of you have swimming pools at home, and when I bought the house I'm in, they had above ground swimming pool, thank God, because I got rid of it after 2 years. Dr. White's not a swimming pool person. Also in Chicago, those 2 summers were like that much time for swimming. But you measure the pH of the water. Important place where they measure pHs to make sure the product is good is any kind of personal care item you use. If you use a skin cream, any kind of skin lotions, chemical companies or the companies that make that measure the pH. They want it close to neutral so it doesn't irritate your skin. Now, let's look how pH paper works. Everybody see YouTube on your screen? Thank you.
Okay, this is the video where we're going to be testing various solutions with pH paper. So you can write down a chart, give this heading or title, testing pH with pH paper. We've got sodium hydroxide base, hydrochloric acid, vinegar, baking soda, lemon juice, window cleaner, Drano, and detergent. Don't worry about that last row. We actually don't have an unknown. So we're just going to test 8 items, okay? They're in the same position on this spot plate as they were in the chart. We're going to use pH paper like this. It'll change color, and we'll match up the color change with what we see on this color chart here to try to determine exactly what the pH actually is. So let's do the first one, sodium hydroxide base. And when we compare it, we can see here, yeah, that's kind of a 12. Next one is hydrochloric acid. And we got a nice pink to red color, so that's, you know, pH 1, probably, yeah. The next one is vinegar, and we get kind of an orange color for this one. That's kind of a 3. We've got baking soda, and we've got a nice green color being produced there, and that's kind of a pH of 8. Lemon juice, and we get kind of like a pH of 3. It might be somewhere between 3 and 4. Window cleaner, which is ammonia, we get kind of a light green color here. It's around pH of 7, but not quite as yellow as what you would see right there. So somewhere between 7 and 8. Then we have Drano, and we get a really dark blue color there. So that's a strong base pH of 12. And then we've got detergent, and that's kind of like a pH of well, it's not quite 9, not quite 10, somewhere between 9 and 10.
And that's how you use pH paper. Now, if you notice from the video, and you can go back because there's a link in the log, the lab, if you want to go see it again, which you can, it's a free country so far. Anyways, pH paper isn't exact, but it's quite good and quick and easy and inexpensive. By the way, the brand they were using, I've never seen another brand. I've used Hydrogen paper, which is pH paper, for decades now. Oops, I shouldn't have said that. But anyways, it's good stuff. Now, there's another way of measuring pH much more accurately, and we call that a pH meter. They're more expensive. You have a probe, you calibrate it, you put it in the liquid. By the way, pH is always in a water solution, not other things, just water solutions. And that tells you the pH by seeing a digital readout, and that's quite good. Remember, pH goes from 0 to 14, never less than 0, never more than 14. If you do, you've calibrated something wrong. Now, in today's lab, you're going to be determining the pH of certain foods that are acidic or basic, or you're going to react in. Now, HA is the standard way of writing an acid. B is the standard way in chemistry of base. So if we have acidic food and a basic food, it's in equilibrium. And for the stuff we're working with, the equilibrium will shift this way, mainly to the right. The KEQ is quite high. Now, if we look on this side, HB plus with A minus is a salt. And what this is called is a neutralization. If I can spell it. And why do we call it a neutralization reaction? Because by reacting the acidic and basic chemicals together, you get the pH close to 7, neutral pH, a neutral solution. And this is what you'll be investigating today. Now, before we go any further, one of the first things we do in this lab, and if we were doing it at COD, you'd be measuring the pH of the water you're using. That's an important thing. DI stands for deionized water. That's water like your tap water, which is put through these special filters that remove ions like calcium and other things that are in our tap water. How many of you have ever heard of soft or hard water? And that's because of ions in there. And you don't want those when you're doing chemistry. When you put it through those filters, that will change the pH. Totally pure water has a pH of 7 at room temperature. You and I cannot get our hands easily on totally pure water. And therefore, I have you measure the pH. And if you look at the lab, you'll see in our lab at COD, our pH of the water going through the filters to make it deionized water has a pH of 6.7. Do I have time? Oh, I do have time. Time for Dr. White's story. I was working for this one company, Borden Chemical. It's now called Hexion. And an area that I was not responsible for in the research development lab was coatings, but my boss was. And at that point, there was a plant we had in Milwaukee and another one in Toledo. And the one in the suburbs of Milwaukee, they wanted to shut down. It was getting old. So they had to transfer all the products and make them in Toledo. Well, the biggest one they made in Milwaukee for GM, our biggest customer, General Motors, they couldn't make right in Toledo. And GM knew about the problem. We told them. And again, I wasn't and all involved in that. And they said you can't shut down that plant until you can make it right, completely right in the other plant. Well, to keep that plant open when we should have shut it down cost the company $100,000 a month. And the people trying to solve this problem, they'd already blown away almost 5.5 months. That's $500,000 wasted. That's not good. Well, anyways, the vice president of R&D, research and development, called me into his office and said, I want you to solve this problem. Because by then I had a reputation for solving problems really quick and good. So unfortunately, my boss, who reported to was the assistant research director, had been trying to solve that problem and he couldn't. And he was upset with me because I was brought in to solve it. Why me? I don't know. Well, it made him look bad. That's why. Because I went in, and here's the important thing about problem solving that one of the great mentors from an earlier company that I worked for taught me, Sid Shapiro, God rest his soul. He died a number of years ago, but at the nice age of 95, but still, oh, did he teach? Because I was fresh out in industry and he taught me a lot. One of the first things he beat into my head was common sense is not common. And throughout my life, I found that's true. And if you think about the common sense, this plant, you can make it, this plant, you can't. Guess what? Something's different. So what did I do? I went to the Milwaukee plant and watched them make it. I also videotaped it. Then I went to the Toledo plant and watched them make it. And I videotaped it. And that took me a couple hours. It wasn't it was only about a 4 or 5 hour process to make this coating. And I went and looked what's different. And it was obvious. First of all, and I won't go into all of it, but one was the water. The water, and I looked at the water and I figured what's something I can measure? Is the water the same? Oh, another thing Sid taught me was never assume or you become the first 3 letters. I didn't say that, but anyways, is the water the same in Milwaukee and Toledo? And the answer was no. And why am I talking about that? The pH of the water in Milwaukee was 7.1. The pH in Toledo in the summer, which is when this happened, was 8.6. Why? That was the worst pH water. It was heavily contaminated. Don't ask, but it was. So there's ways of adjusting it, bringing the pH in and doing a couple other things. Within about a week, I solved the problem. They made it right. And my boss, the research director, was very happy with me. My boss was really mad at me because I made him look bad. He should have figured that out. And because he didn't, other chemists working for him in another research group, the company blew about $500,000, and the president of the company wasn't happy with my boss. He was happy with me, but that's the Dr. White story. All right, today we're going to be using some very dangerous chemicals, and if we were in the lab, I'd say make sure you have proper safety goggles on, which we do in all labs at COD, and your gloves on, because one of the dangerous chemicals, it's show and tell time, is this. Yep, they're chemicals. And if you look at the label right here, it says tomato concentrate that has an acid in it, citric acid, and distilled vinegar. And distilled vinegar is water and acetic acid. So this is acidic. But we don't do this, and I bring this in, but another one that's better. If you haven't used Sweet Baby Ray's honey barbecue sauce, you're missing a lot in life. Do I get paid for product placement? I wonder if I can get money from them. Hey, buy this product. Dr. White says that. Nah, they won't. And if we look at the label here, it says high fructose corn syrup. If you're taking my organic chemistry, I tell you that's just another name for cheap, inexpensive, very sweet sugar. And the next thing is distilled vinegar. Remember, vinegar has acid, acetic acid, and water. So think about it. Ketchup or barbecue sauce you're making your food acidic. I bet you never thought you were doing that when you're putting it on your French fries or whatever. This is better than this, but some times this works. This and horseradish is really good with shrimp. You make your own cocktail sauce and it's cheaper. All right, let's look at today's lab. First of all, you measure the pH of DI water, which I gave you. Everybody see today's lab now? Thank you. All right, now in part 2, you'll be reacting different food items, really condiments and other things, with sodium bicarbonate. And the reaction is any acid, like in the ketchup, plus sodium bicarbonate, which is baking powder, is in equilibrium, but it's mainly to this way because it has a very high equilibrium constant. You'll get a salt plus water plus carbon dioxide, and the arrow up means it's a gas. You see bubbles. And this part, you'll be reacting sodium bicarbonate, which is a weak base, with different acids in food. And you'll initially measure the pH of the food before you react it, and then after each addition of sodium bicarbonate. And if we were in the lab, we'd add some water in a beaker, it's easier, or a test tube, but a beaker is easier to clean out later on. You put a small amount of food, you'll measure the pH, then you'll add small amount of baking powder. This one we don't weigh out, I show you in the lab. This is a small amount, the tip of a spatula. Mix it for a quick amount. Reactions of acids and bases are the fastest in all of chemistry. And then after about 30 seconds to a minute, you measure the pH. Then you add a little more and you mix it again, measure the pH, and finally, to have fun, we dump a whole lot more in there and measure the pH. And here, for some reason, I don't know why the things you'll be measuring are vinegar, orange juice, ketchup, tomato paste, that's dangerous, it stains clothes if you're not careful, lemon juice, mustard, and Coca-Cola. And you would measure the pH. Now, let's have some fun. Everybody see YouTube on your screen? Thank you.
Okay, take number 3. This time, we've got a mixture of 1 cup vinegar to 1 cup warm water in a 2-litre drinks bottle with our launchpad system here. This time we're putting the baking soda inside a pop sock that's made out of tights. Now hopefully that will mean that the vinegar can get inside the pop sock more easily and it won't get wedged in the end of the bottle when it's about to go off, which should mean the gas gets out more easily. Here we go then. So cut a little hole in the pop sock there. We're drying out, we should be able to reuse this actually. Very gently, make sure the inside is dry. We're going to feed our bicarb in the pop sock through the gap. Once we've got bit in, we should just be able to gently dip it in through, push it on down. Right, now we've got the interesting bits. So put the bottom in the right place, ready to run back very quickly. Launch pads ready with the cork. Here we go, and oh, it actually suspends it. That's a nice feature. Ready? 3, 2, 1. Over we go. Bubbling away nicely. Pop sock looks like it's turned into a balloon. Oh, that's definitely better delivery methods. Look at it go. Oh. That's very frothy. That's very frothy.
Whoa! Oh, success!
It's the pop sock.
Right, pop socks forever.
I hope you enjoyed that. Don't try it at home unless you have safety goggles and all that. But if you want it carefully in a sink, how many of you have done vinegar, baking powder, volcanoes for your kids, or mix them together? Do it in the sink, put a little together, and it'll fizz up. And that was the reaction I showed you. Now in the lab, you'll record the results. And here, like for vinegar, the initial pH was 1. Then after you add, you'll see, I should have, this should be clear. First column, I made a mistake. But anyways, after the first addition, you see bubbles and the pH is 3. After the second addition of the sodium bicarbonate baking powder, the pH is 5. And then after a lot more, it goes up to 7. And you can see different items in your kitchen have different pHs, which if you notice are all less than 7, and everything in this list is acidic. Have you ever thought of all the condiments you put on a hot dog are acidic? Anyways, that's part 1. In part 2, we'll do the same thing with now a different base, sodium hydroxide. And this is an equilibrium, but the equilibrium constant is so high, it's shifted to the right, and you'll get a salt plus water. And now you'll do the same thing in a beaker, put some water, put some of the food, add a few drops of, oh, you know what a 0.10 capital M NaOH solution is. That's a 0.10 moles per liter sodium hydroxide solution. You'll mix it, measure the pH, add 2 more drops, and then add 10 drops. And you're doing similar to what you did in part 1, and the same items, food items. And here, if we look at table 3 or part 3 here, results, vinegar initial pH is 1. It was clear after addition of the sodium hydroxide. Again, you're neutralizing some of the acid, making the pH go towards 7. You have 5, add some more, you add, go up to 7, add a lot more. Wow, you're up at 13. That's very basic. And you see the rest of it. And then we have the questions, and notice it has the dreaded question part of a question. Please include an explanation for your answer, and other questions. And that's today's lab. And with that, I'm done. And I can say, have a great weekend. Gehen gesund. Goodbye. If you have any